Hello, I welcome you all in this presentation related with the subject fundamentals of the manufacturing processes, and we are talking about the processes which are used for improving the properties and mechanical performance of the different metal systems which are used for manufacturing variety of engineering components. So, in the heat treatment of the steels, we have talked about the iron carbon diagram, which is used for identifying the temperature identifying the maximum temperature up to which steel should be heated and then thereafter we need to see how long it is to be held at that high temperature, and then what kind of cooling rates we should use. If we see heat treatment of the steels typically follows this kind of cycle, wherein first it involves the heating, wherein there will be increase in temperature as a function of time. Then the steel is held at a constant temperature for some time. This is called soaking. Soaking basically done for producing the homogeneous austenite, so that it is available for the transforming into the desired phases, and then as per the kind of the properties and phases desired, the different cooling rates are applied. For example, the very slow cooling rates are used for the annealing purpose, which basically softens the metal and reduces the hardness, and then it is also used for normalizing purpose, which refines the grain structure, reduces the residual stresses, increases the strength and hardness, and this is called quenching, or this is also known as hardening, wherein the purpose of which is basically to achieve the high hardness and increase the strength. So, the very coarse perlite is produced when annealing is performed, and fine perlite and the fine bainite is used is produced when the normalizing is performed, while the target is to produce the martensite, which is very hard, so that the strength and the hardness of the steel can be enhanced. So, this is the typical heat treatment cycle which is used for heating, soaking, and then controlled cooling as per the requirement of the properties, so that the suitable phases in the steel can be produced in order to have the desired set of the properties. So, the second step after identifying the maximum temperature up to which steel should be heated, the next step is to find out how to soak it. Soaking, depending upon the plain carbon steels, as I have said, plain carbon steels will be having ferrite, alpha, maybe perlite, or it may have the perlite plus cementite mixture. These are the three phases. This is for the hypereutectoid steels having the carbon content greater than 0.8. This is for the eutectoid steel having just 0.8% carbon, and alpha plus perlite is produced in case of the hypoeutectoid steels. So where in the carbon content is less than 0.8%. So, depending upon the carbon content in steels, the different phases are found at the room temperature. This is what is the case of the carbon steel or plain carbon steels, while in case of the alloy steels, depending upon the kind of the alloying elements which are present, there may be presence of the vanadium carbide, tungsten carbide, molybdenum carbide, and titanium carbide, etc. These are very hard and very stable, and stability of each type of carbide is different. So, they take longer to get decomposed. So, the time required for homogenization of the steel. So, in this case, apart from these carbides, depending upon the carbon content, it may have alpha plus perlite mixture, or it may have alpha plus perlite plus carbide mixture. So, and even if like say in a steel, if there was one carbide particle like chromium carbide, and when it decomposes, it will be producing the chromium and carbon. So, but that they will remain here. So, this is the region where it will have higher carbon concentration, higher chromium concentration in the steel at a particular location. So, wherever these carbides are there, if they decompose there, when they decompose at a particular location, that region will have the higher chromium or higher vanadium or higher molybdenum with the higher concentration of the carbon. So, this still it will, they have got decomposed, but it will be inhomogeneous, because the concentration of the allying elements and concentration of the carbon will be more at few locations where these carbides were present, and it will less at other locations. So, in steels it is important that after the heating, means heating at a particular temperature and then soaking, homogeneous austenite is produced in order to have the desired effect on the transformation, so that the desired phases can be achieved for the heat treatment purpose. So, with regard to this, with regard to the composition of the steels and the presence of the different phases, it takes different time for homogenization purpose, and that is what we can see schematically with the help of diagram, which will help us to understand how the soaking time can vary with the change of the steel and with the change of the phases which are present in the steel. So, it goes in like this. This is a schematic diagram. In y axis we have temperature of soaking being used in degree centigrade. Say it is greater than 730 degree centigrade, and in x axis we have the time scale may be in minutes. So, say at the room temperature, when it has not decomposed initially, what it will be having, say this is at a room temperature. So, at what it will be having at room temperature, consider the alloy steel or carbon steel. So, in case of the alloy steels, what will be having at room temperature? Ferrite, perlite plus carbides. So, when the steel is held for some time above the upper critical temperature limit, like say 800 degree centigrade or more, above the upper critical temperature limit, which will start from the 730 to 910 degree centigrade. So, depending upon the carbon content, for 0.8 the upper critical temperature limit happens at 730, while for very low carbon content like 0.02 or even less, it is 910 degree centigrade. So, whenever the steel is exposed at a higher temperature above the upper critical temperature limit, initially at room temperature, what it has? Alpha, perlite and cementite. When it is exposed above the upper critical temperature limit, it starts getting decomposed. So, first of all the perlite decomposes into the austenite. So, it retains first retains the ferrite and the cementite, plus perlite gets converted into the austenite. Thereafter, it is the turn of the ferrite to convert into the austenite. So, carbide will remain stable, and alpha will also convert into the austenite. So, now the cementite ferrite and the perlite have converted into the austenite, only the carbides are left. Now, the carbides will decompose into the carbides will decompose and they will form inhomogeneous composition of the austenite, because this inhomogeneous composition due to the higher concentration of the allying elements and the carbon at the location where these carbides were there. So, it will be leading to the presence of the inhomogeneous carbon content and allying concentration. Further, if we give more exposure, then it will have the homogeneous austenite. So, these are the kind of the zones which are formed. What it shows, that if the exposure is given at low temperature, it will take longer as compared to the case when it is done at a higher temperature. So, if we see the temperature is this, so at this temperature it will take this much time in order to get the homogeneous austenite, and if the temperature is high, at high temperature it will take less, because all the phases will be getting converted into will be converting into the austenite, and then they will be producing the homogeneous austenite much earlier. So, higher is the temperature, lesser will be the time it will take to produce the homogeneous austenite. So, this time may come like 30 to 60 minutes depending upon the kind of the steel composition being used, and then 30 minute is added additionally for each 25 dimension. So, initially the depending upon the kind of composition of steel, 30 to 60 minutes time it may take, so that homogeneous austenite is produced. Now, we if we consider just there is no alloy carbides, just the ferrite and pearlite is present. In that case, what we will see that the first alpha plus pearlite. So, pearlite will convert into the austenite, and then this alpha will also convert into the austenite. So, this will be inhomogeneous, and then we will get the homogeneous austenite. So, what we can see here, in this case it will be achieving much earlier the homogeneous austenitic state, because it does not have the carbides to decompose and then to produce the homogeneous austenite. So, and therefore, the plain carbon steels needs the lesser soaking time as compared to the alloy steels. So, in the heat treatment, after identifying that maximum temperature up to which steel should be heat treated, the time for which it should be soaked for homogenization of the austenite, the next step is to have the controlled cooling, so that the desired set of the phases and the microstructures can be obtained in order to have the desired set of the properties, and this is realized through the set of the two types of the diagrams. These are called one is called triple T diagram or isothermal transformation diagram, and another is continuous cooling transformation diagram. So, as its name appear, isothermal transformation diagram, this is also termed as isothermal transformation diagram, where or isotemperature transformation diagram, which means that the transformation will occurring at the constant temperature. So, since this kind of the diagram, both these diagrams are sensitive for the steel composition. So, the simplest diagram is for the eutectoid steel, means where austenite converts into the pearlite on cooling, and on heating pearlite converts into the austenite. So, the relationship we will see in terms of the time here is in second, and it is in the log scale, say 0.5 second, 1 second, then 10, 10 to the power 2, 10 to the power 3, 10 to the power 4, like this. And in the y axis we have the temperature at corresponding to the different values, say 900, 800, 700, 600, 500, 400, like this, say room temperature. It is the temperature in y axis in degree centigrade. So, what we see that when the steel is heated to the homogeneous austenitic state, what happens when it is exposed to the different constant temperature values. Since the steel upper critical temperature limit, say for the steel is, for a given steel is 800 degree centigrade. So, there will not be any transformation above the below, there will not be any transformation from the austenite to other phases above the 800 degree centigrade. Above the 800 degree centigrade, it will be completely in austenitic state. So, this is the homogeneous austenitic state. So, as soon as it is held at a lower temperature, we will see that transformation will start into the other phases, like this. So, this is what we can see, a typical diagram which is obtained like this. So, these are the two lines corresponding to the pearlite start transformation and pearlite finish transformation, PS and PF, corresponding to the 100% pearlite and corresponding to the 100% austenite. So, this is the line above which on the left side of which there will be 100% austenite. So, when the say steel heated the bar is heated say into the homogeneous austenitic state and say capped at a 700 degree centigrade or 750 degree centigrade, say capped at 750 degree centigrade. So, what happens, say this is the line corresponding to 750 degree centigrade. So, on holding at the 750 degree centigrade, there will be no transformation of the austenite up to this much time, and thereafter it will start transforming into the perlite. So, here this is the perlite transformation starts, and transformation from the austenite to perlite starts, and here transformation from austenite to perlite is finished. Between this we may have another line corresponding to the 50% transformation line. So, this is corresponding to the 50% transformation from austenite to the perlite. Here we will have the complete transformation of the austenite into the perlite. So, this is about the transformation occurring at a constant temperature. If we see same thing, if the exposure is given at say 500 or 550 degree centigrade at constant, same bar heated to the homogeneous austenitic state and held at say 500 or 550 degree centigrade, then what will set? What we will get? The transformation will be occurring after this much time, and then transformation will be completing after this much time. So, this is the temperature at which the transformation is starting earliest and if ending at the earliest. So, this is called the nose of the, this one is called the nose of the triple T diagram, and this shows the temperature at which it will take minimum time to start and end the transformation. And below this, if we further go to the lower temperatures, then what we will see, the transformation will start after a further longer period, and then it will take further longer period into the different phases. So, if we see corresponding to this diagram up to this nose temperature, what we get basically the perlite. So, the perlite is coarse when the transformation is done from austenite to the perlite at a high temperature, and perlite perlite is fine when it is done below the means near the nose temperature. Below this, upper bainite is fine, upper bainite is formed, and further lower temperatures fine bainite is formed. If we see this is the temperature of martensite start, and this is the martensite finish temperature. So, this is the temperature below which if the steel is quenched then or cooled, then it will be leading to the martensitic transformation, austenite to martensitic transformation. So, this is the martensite start formation line, and this is martensite finish transformation line. If we see, so here we will have the martensite finish. So, and then we will have, this is the martensite start transformation line. So, here if we try to see how the hardness and the strength will be changing, so that is what we can see from this diagram. Like hardness is very low when it is like say 10, then for the coarse perlite, and then for fine perlite it may be like RC 20, then for bainite RC 30, then RC 40, and then it may be RC. For fine bainite actually it is RC 50 to 60. So, 50, this may have 40, and this may have 30, and this we may have 20. So, if we see, it will be increasing with the change of the phases which are being formed at the constant temperature. And if the martensite is formed, if we quench directly from 900 degree centigrade to this temperature, then we will see that martensite is formed, and at this temperature as a function of time how the martensite is formed, this is what we can see here. Here like say the MS temperature and MF temperature, and here we have the fraction of the martensite being formed. So, this is what we can see, the 0 fraction and 100% fraction. So, this line basically starts like this. So, initially the formation is very less, as the quenching is done and at MS temperature, then it will keep on increasing. Say this is corresponding to the 50% transformation and 100% transformation. So, when the quenching is done at MF, all the austenite converts into the martensite, leading to the 100% of the martensite, and when it is just finished quenched at MS, it will have the 0%. Then with the decrease in temperature of the quenching, the fraction of the martensite being formed will keep on increasing. So, this is always higher. It may have, as per the composition, this value may be from 200 to the MF, maybe like say the room temperature, or even below minus 10 degrees centigrade. So, these are the functions of the composition. So, lower is the temperature. If the steel is quenched from the austenitic state to the lower temperature, it will be leading to the more fraction of the martensite, and which in turn will be increasing the hardness of the steel. So, maximum hardness which is achieved by the steel, like say it is the 60 to 65. Again, it will depend upon the carbon percentage which is present in the steel. Say for 0.2 to 0.8% carbon content in steel, when it is hardened, what we get? Increasing hardness level, like say from 20 HRC to the 60 or 65 HRC. So, with the increase in carbon content, when a steel is quenched, we get the increasing percentage of the increase in the hardness of the steel and increase in strength of the steel. So, maximum hardness which is achievable even after the hardening, like martensitic transformation, it will be that will be the function of the carbon content present in the steel. Now, if we just superimpose the cooling rates, because these transformations will be occurring at the constant these transformations are corresponding to the constant temperature, but what if the steel is quenched, cooled at the and steel is cooled at the different rates instead of exposing the steel at a constant temperature. So, transformation diagram actually helps us to see what if the steel is exposed to the different constant temperatures in austenitic state. So, what kind of phases will be obtained, but actually we apply the different cooling rates. That is what we can see here from like 1, 10, 100, 1000 and 10,000 seconds. It is at the time in x axis. So, when the continuous cooling is applied, what we get? We get a nose. This is the portion of the CCT diagram. This is the temperature. This corresponds to the like say 550 degrees centigrade roughly, and this is the MS temperature. This is MF temperature, which will be indicating that how at what temperature the martensitic formation will start. So, from the austenitic state, when the steel is cooled at the different rates, so what we get here at one rate, another rate, third rate, fourth rate, like this. So, these are the 4 cooling rates. So, here in this case the transformation will occurring in this zone, here transformation will occurring in this portion, and whatever portion is left, then transformation will occurring in this portion. Here transformation, because whole of the austenite has converted into the perlite. So, no transformation will be occurring further. So, this is the zone of the transformations. So, when the cooling rate is slow cooling rate results in the transformation of austenite into the coarse perlite. Here it will be leading to the fine perlite. Here it will be the mixture of both. Here we will have the perlite plus martensite, and here whole of the austenite will be transforming into the martensite. So, this is the minimum cooling rate in order to form. This is the minimum cooling rate that must be applied to transform whole of the austenite into the martensite. If the cooling rates are lower, for example, cooling rate is lower, then it will first form the austenite, first form the perlite, and thereafter remaining austenite will be forming the during the cooling from between the temperatures MS and MF. So, remaining portion it will be forming the martensite. So, martensite and perlite will be the 2 phases. So, since the perlite is softer phase as compared to the martensite, and therefore, if you want a complete increase, means if you want hardening only, then soft formation of the soft phases is avoided, and for that cooling rate must be, minimum cooling rate must be greater than the cooling rate which is able to bypass the nose of the CCT diagram. So, this is called critical cooling rate. Critical cooling rate is the minimum cooling rate that must be applied in order to transform the austenite into the martensite, and this critical cooling rate is a function of the three factors mainly, and these are basically related with the, like the nose of the TTT diagram may be like this, or it may be here, or it may be very close to the axis. So, in this way. So, these are the functions of the three aspects. One is the carbon content, the second is the grain size of the austenite, third is the homogeneity of the austenite. So, means the composition of the steel, grain size and the homogeneity, and this grain size is basically affected by the soaking temperature. Higher is the soaking temperature, coarser will be the grains. So, if we see with respect to this, carbon content or the alloying concentration is the most significant factor. If this is say for 0.8% carbon, so for 1.2% carbon, the nose will be shifting towards the right, and which in turn will be decreasing the critical cooling rate. So, it will be easier to transform even using the lower cooling rates to austenite. Transformation of austenite into the martensite will be easier even using the lower cooling rate as compared to the cooling rate which will be required for this one, and the cooling rate transformation of austenite to the martensite may not be possible in case of very low carbon content steels. Hypoelectric steel, even if it is formed, then it will be of the very low hardness. So, this critical cooling rate is a function of the composition predominantly, but thereafter if it is heterogeneous austenite is being used, then the sum of the alloying elements and carbon content may not be there in the homogeneous solid solution of the austenite, and then in that case they will not be able to have their effect on the nose of the CCT diagram. So, if it is homogeneous, then effect will be good, and say this is the case when it is heterogeneous, then that will be leading to the further lower side, means it will be shifting to the right side, left side. So, if we consider the one case for one steel, this is for homogeneous, and if it is heterogeneous, then it will be shifting towards the left. So, it is always good that homogeneous austenite is formed, and the similar kind of the trend happens when the fine grain size is used. Say when the grain size is coarse, there are few locations for transformation of austenite into the other phases. When the grain size are fine, the transformation starts earlier. So, this is the case for the fine, and this is the case for the coarse. So, the actually coarse grains lower the critical cooling rate, while the fine grains increase the critical cooling rate. So, from the hardening point of view, it is always preferred to have the coarser grains which can be realized through the higher soaking temperatures. So, using these three diagrams like iron carbon diagram and then temperature versus time diagram for obtaining the homogeneous austenitic state and continuous cooling diagram, we can design the suitable heating temperature, maximum heating temperature for heat treatment purpose, soaking time for heat treatment purpose, as well as we can design suitable cooling rates. So that desired phases can be obtained in form of coarse perlite, fine perlite, fine bainite or coarse bainite, and or the martensite during the heat treatment of the steels. Now we will take up one the typical heat treatment of the steel, which is extensively used for the different purposes, heat treating of the steels. This is called annealing. Annealing is basically used for inducing the softness in the steel, and it also lowers the hardness. It sometimes, if it is properly controlled, then even it can refine the grain structure. It improves the electrical and magnetic properties of the steels, and because of the reduction in the hardness and inducing the softness, especially in case of the high and medium carbon steels. High and medium carbon steels, annealing helps to improve the machinability. It allows the machining easily, but in case of the low carbon steels, annealing leads to the tearing or very lengthy chips, which will adversely be affecting the machining behavior of the steels. So, there are three variants of the annealing of the steels. One is called full annealing, another one is called process annealing, and third is spheroidizing. So, about these what we will be doing, like full annealing, spheroidizing, and process annealing. And there is one more, stress relieving. These are the four variants of the annealing of the steel. So, with regard to the iron carbon diagram, what we do, this is the upper critical temperature limit. So, if we take one particular composition of the steel, so it is heat treated above about 50 degrees centigrade above the greater than the UCT for a given steel. So, we will be heating up to this temperature for homogenization purpose as per the dimensions of the control dimensions of the component to be heated, and then considering the CCT diagram for the annealing purpose, we use the cooling at a very low rate. So, what we do in the furnace being used for the heat treatment purpose, we heat it. After soaking, the furnace is closed, so that heat loss takes place at very low rate. The objects to be heat treated are will be experiencing the lower cooling rates, and that in turn will be leading to the annealing, because for annealing we need very low cooling rates, and when it happens it will be leading to the formation of very coarse perlite. So, and coarse perlite will be resulting in the very low hardness of 10 to 20 HRC as per the carbon content in the steel. But whenever the annealing is done, the fresh grains will be formed, so that will be leading to the recrystallization. So, this kind of the recrystallization will be leading to the loss of any strain hardening effect if it was there. But when the annealing is performed on the low carbon steels and the medium carbon steels, then it results in the alternate layers of the ferrite perlite. So, like say this is ferrite, cementite, ferrite, cementite. So, basically the spacing between the ferrite and perlite, ferrite to ferrite phases or ferrite to cementite to cementite phases is used to define the coarseness or fineness of the fineness of the perlite. If the ferrite and perlite are very closed, layers or lamellas of the ferrite and perlite are very closely packed, then it will be resulting to the fine perlite, much better mechanical properties as compared to the case when they are widely spaced. So, in case of the coarse perlite, the spacing will be wider as compared to the case when the fine perlite is produced. So, fine perlite is produced with somewhat higher cooling rates, and this is the typical case of the normalizing heat treatment. But when the annealing is performed, means the lower cooling rates are applied for the hyper eutectoid steel. Hyper eutectoid steel means the carbon content is greater than 0.8%. So, in that case, as per this diagram what we have seen earlier also, what will be having the 100% perlite at 0.8, reducing fraction of the ferrite 100%, this is 0%, and yeah, this is 0 and this is for carbon content, this is 100%, so 100% ferrite, and then ferrite at 0.8, perlite is 100%, and thereafter what we see, Fe3C. Fe3C starts appearing for the hyper-eutectoid steels. So, in case of the hyper-eutectoid steels, whenever annealing heat treatment is done, the very thick plate of the Fe3C starts forming. So, Fe3C plates are formed at the grain boundary, and the remaining one will be the coarse perlite at all other places. So, the coarse perlite plus the thick layer of the Fe3C. Since the Fe3C is very hard and brittle, and if it is formed continuous network along the grain boundary, then it reduces the strength of the steel. So, that is why what we see here, the some reduction in the strength of the hyper-eutectoid steel takes place after the annealing. Further, during the machining, such kind of thick layers causes the interrupted irregular shock loading onto the cutting tool during the machining. Since if the thick layer of the cementite is present during the machining, then the soft metal will be easily machined, but as soon as the tool comes across the thick layer of the cementite, which is very hard and brittle, it causes the shock loading onto the tool. So, that may lead to the fracture of the cutting edge. This factor basically reduces the machinability of the steels. That is why for hyper-eutectoid steels, full annealing is not is never a final treatment, but for improving the some other characteristics, full annealing may be performed, but not at the final stages. Another heat treatment is the spheroidizing. As we have seen, this is primarily applied for the hypo-eutectoid steel. When full annealing is applied to the hyper-eutectoid steel, it forms the thick layer of the cementite, which reduces the machinability. So, in order to improve the machinability, one special treatment which is called spheroidizing is applied, and spheroidizing is applied using 3 approaches, wherein this is the lower critical temperature. So, steel of a given composition, say like this for high carbon steels or for hyper-eutectoid steel. In both the cases, here in this case Fe3C will be there with the perlite, and here alpha plus perlite, these are the things which will be there. So, when it is applied for hyper-eutectoid steels, what will be having the thick layer of the cementite present at the boundary, this will be adversely affecting the machinability. So, efforts are made in order to break this thick layer of the austenite, thick layer of the iron carbide, and for that purpose what we do, we hold the steel just below the lower critical temperature limit for longer time. So, one method of spheroidizing is the long holding of steel below lower critical temperature, just below the lower critical temperature limit, and another is the alternate heating cooling at just above heating above the lower critical temperature and then cooling. So, heating and cooling about lower critical temperature limit. When these are the 2 approaches, when they are applied, what happens, all this cementite is broken down and it gets spheroidized. So, the layers get lamellas of the Fe3C gets spheroidized in form of the spherical balls, and which allow easy machining. So, basically embrittlement happening due to the Fe3C is reduced by the spheroidization of the Fe3C. So, these Fe3C and the remaining matrix is of the ferrite. This is what is achieved, and when it is done, it helps to realize the improvement in the machinability. So, now I will summarize this presentation. In this presentation, basically I have talked about the two additional aspects related to the principles of the heat treatment. One was the triple T diagram, and the second one was the continuous cooling diagram. Using these two diagrams, we can identify how to determine the cooling rates for obtaining the desired set of the microstructures. Additionally, I have also talked about one heat treatment process used for the steel is annealing. So, what is the effect of annealing and how the properties are modified in the annealing process. Thank you for your attention.